Let's draw some more Lewis structures. Let's practice this. Draw a Lewis structure for CH4. CH4. So I know that means there's 1 carbon and 4 hydrogens. The very first step, if you follow the steps for drawing Lewis structures, you'll never go wrong. The first step is to figure out how many atoms you have. 1 carbon, 4 hydrogens. And then you have to figure out how many valence electrons they bring to the party to share. And you need a periodic table to do that. So let's go look at our periodic table. Here's carbon in group 14. How many valence electrons does each carbon atom have? 4. 1, 2, 3, 4. It's 4 over in its period, where you can look at the last digit of the group number, 14. Hydrogen has 1 valence electron. That's pretty simple. So I know that each carbon brings 4 electrons. Each hydrogen brings 1 electron. I need to add up the total number of electrons that have been brought to my party. 1 times 4 is 4. 4 times 1 is 4. Add that up, I get 8 total electrons have been brought to my party. And then I'm going to draw the structure. If you have carbon in the molecule, it will always go in the middle. Carbon loves to form bonds. It loves to form 4 bonds. It loves to share 4 pairs of electrons. And then you're going to arrange the other atoms around it on each side, on every side. So imagine there's do not draw this, but imagine there's a box around carbon. Then I would put a hydrogen on this side. Remember, I have 4 of them. And then here, and then there. So I'm going to surround it with the other atoms. 1 atom on each side. And then I'm going to use dots to represent the electrons. Trying to remember that a covalent bond is a shared pair of electrons, where carbon wants 8 total and each hydrogen wants 2. So I'm just going to try to distribute these 8 electrons in my molecule to make everybody stable and happy. So carbon, I'm going to have 8 electrons. Notice that I can only put 2 electrons on every side. Remember how I had that box drawn? Each side of the box can hold a maximum of 2 electrons. That's just how these diagrams work. So I've distributed 8 electrons, 2 on each side. And now let's see if this makes sense, if everyone is indeed stable and happy. Let's look at this hydrogen. Is it happy? Does it have how many electrons does it have the number of electrons that it wants? Yeah, hydrogen is happy with 2. And look, hydrogen has 2 right now. How about this hydrogen? Yes, indeed, it has 2. This one has 2. This one has 2. What about carbon? How many electrons does carbon want? Like most other atoms, it wants an octet. It wants 8. Is it happy and stable? Yes, it is. It has 2, 4, 6, 8, just like we saw earlier. You don't need to draw the circles on your Lewis structures. That's just to help you kind of check your work to see, is everybody happy? The hydrogens each have a pair. They each have 2. The carbon has 2, 4, 6, 8. It is good to go. I have arranged the electrons to maximum to a side. I have used 1 carbon atom, 4 hydrogen atoms. I have used the correct number of electrons. I only had 8 electrons, 8 valence electrons available to me. Carbon brought 4. Each hydrogen brought 1 for a total of 4. That's a total of 8 valence electrons. I've only used that number. When you draw Lewis structures, you're always asking yourself these questions. You're always checking your work. Is everybody stable and happy? Have they received the number they want? Carbon wants 8, each hydrogen wants 2. And have I used the appropriate number of valence electrons I actually had available to me? And then every pair of electron that is being shared between atoms, you're going to redraw as a dash. And that dash represents what, ladies and gentlemen? Yes, indeed, it represents a covalent bond. So you can see that right here, there are 4 covalent bonds. This is my Lewis structure. Yay. Let's do 2 more. Let's do 3 more. So I have, remember, you want to figure out, first of all, how many total valence electrons you have available. I have 2 hydrogens. They're bringing 1 electron each for a total of 2. 1 oxygen. Oxygen is in group 16. It has 6 valence electrons. Remember, I'm just worried about the valence electrons. So it brings a total of 6. I have a total of 8 valence electrons. I don't have carbon, so I don't know what really to put in the middle. Well, another rule of thumb is, generally speaking, molecules like to be symmetrical. So how can I make this symmetrical? I know, I'll stick oxygen in the middle, and then I'll stick my hydrogens kind of out to the side like this. And now I'm going to go around and distribute these 8 valence electrons, trying to make everybody happy. So I'm going to give 2 here, 1, 2, 3, 4, 5, 6, 7, 8. This is a Lewis structure. Notice that I only have 2 maximum per side. Does this work? I need to check. Is everyone stable and happy? Well, hydrogen is stable with 2, and it doesn't need to have 2. It's sharing them with oxygen. This hydrogen is doing the same thing. So the hydrogens are stable and happy because they have 2 electrons. Is oxygen stable and happy? Has it reached his potential energy minimum by achieving an octet of electrons, of valence electrons? Yes, indeed. It has 2, 4, 6, 8. So by sharing, everyone is happy. And I would redraw this just like this. H, O, O. And if you want, you can draw those. We refer to these unshared pairs right here. We refer to them as lone pairs because they're not shared. So there's my lone pairs of electrons. How many covalent bonds are in this molecule? 1, 2. Remember, our definition of a covalent bond is a strong chemical bond, a strong electrostatic force formed along a shared pair of valence electrons. This is a shared pair because it's in between these 2 atoms. This is a shared pair, it's in between these 2. These are not shared pairs, they're lone pairs. So this molecule has 2 covalent bonds and 2 lone pairs of electrons. And this is what a water molecule would look like, more or less. Let's do a few more. F2. So fluorine, I have 2 fluorine atoms. Remember, the first step is always figure out your total number of valence electrons. Each one brings 7 electrons. Fluorine is a halogen. It's in the group right before the noble gases, group 17. So I know that it has 7 valence electrons. I have 2 fluorines in my molecule. So I have a total of 14 electrons. So now I'm going to draw out those 2 fluorine atoms. I have no other choice except for to draw them side by side. And then I'm just going to take my 14 electrons and see if I can make everybody happy. 1, 2, 3, 4, 5, 6, 7, 8. They're sharing those 2, so I don't need to draw any more on this one. 9, 10, 11, 12, 13, 14. So remember, what 2 things am I always checking? Have I used the appropriate number of electrons, and do all atoms have an octet? Well, I have indeed used 14 electrons, haven't I? 2, 4, 6, 8, 10, 12, 14. Yay, I've used the correct number. Is everybody happy and stable? Well, let's check. Does this fluorine have an octet? It sure does. 2, 4, 6, 8. Yay. Does this fluorine have an octet? It sure does. 2, 4, 6, 8. Yay. And I've only used 14 electrons. So by sharing, I can get them both to have an octet using only a total of 14 electrons. How would I redraw this? Just like this, with an F, a dash to represent that shared pair of valence electrons. What is a shared pair of valence electrons really? It's a covalent bond. And of course, I could draw the lone pairs. How many lone pairs are in this molecule? Remember, lone pair is a pair that's not shared. So 2, 4, 6, or excuse me, so 1 pair, 2 pair, 3 pairs, 4, 5, 6. 6 lone pairs and a single shared pair, a single covalent bond in this molecule. Let's do one now for O2. I have 2 oxygens, each one bringing 6 electrons to the party. Therefore, I have a total of 12 valence electrons. I'm going to go through and distribute my electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, crap. By trying to make them both happy with an octet, this oxygen has 8 right now, and this one has 8 right now. I've broken my rules. I have not used 12. I've used 14. I've used too many. Crap. Is it impossible then for these 2 atoms to bond together to form a molecule? Because if they come together, they only have 12 electrons amongst them, between them, to share. And that doesn't work because To get them both stable and happy with an octet, sharing a pair of electrons, I need 14 to do that. Is there something else these two atoms could do? There is something else they can do. What if instead of sharing a single pair in the middle, what if they shared two pairs? So now I would have to do 1, 2, 3, 4. Now think about it. How many valence electrons does this oxygen atom have right now? It has 2, 4, 6, 8. It already has 8. I don't need to draw any more down here because it's already stable and happy. This one has 2, 4, 2, 4, 6, 8. This one also has 8. How many total have I used? 2, 4, 6, 8, 10, 12. Aha! I have used now the correct number of electrons, and I have achieved an octet for both my atoms. This oxygen has 2, 4, 6, 8 valence electrons. This one also has 2, 4, 6, 8 valence electrons. They are sharing two pairs. So I would redraw that like this. Not just one dash in the middle, but two dashes. Draw my lone pairs. Any guesses as to what we call this? Yes, we call it a double bond because it is two covalent bonds. It literally is a double bond. They're sharing two pairs. They've doubled up on their sharing. How do you think the strength of this bond compares to a normal single bond like we've been looking at? Like in the last example, where these two fluorine atoms were bound together with a single bond. Which bond do you think is stronger? Of course, the double bond is stronger. Double bonds are stronger. So sometimes when you're drawing your Lewis structures and it doesn't work out, remember why did we have to do this? Because when we did it originally and we tried to get them to have an octet just by sharing a single pair, that used 14 electrons, which was very sad because we only had 12 available. So if this ever happens, sometimes you've got to try to double up on your sharing. If you get them to double up on the sharing here, you get to take a pair away from this one, take a pair away from this one. That's basically what we did. And now I've used 2, 4, 6, 8, 10, 12. I've used 12 electrons, which is the number that I had available. And like you can see right here, the oxygens are both stable and happy with their octet. These are Lewis structures, and you must be able to recognize how many bonds, how many lone pairs. How many lone pairs are in this molecule? 1, 2, 3, 4 lone pairs, 2 covalent bonds. How do I know that O2 is a covalent structure instead of an ionic structure? How do I know that all these are covalent? Because they're all nonmetals. Nonmetals bonding with nonmetals. That's the definition of a covalent structure. By sharing valence electrons to achieve that octet. Could I break these bonds easily by, say, heating up this substance to a boil or something? No, you can't. Chemical bonds are not easily broken. Well, what gets broken when you boil water? Let's say that here is a water molecule, and here is another water molecule. And I have a large collection of water molecules in my pot of water. What gets broken when I boil it? Am I breaking the strong chemical bonds right here and separating the atoms? No, I am not. That takes a lot of energy. Those bonds remain intact even when you boil water. So what are you breaking when you boil water? Yes, you are breaking the weaker intermolecular force. So once again, do not get the strong chemical bond, of which we've learned two types, covalent and ionic. This is covalent because it's shared pairs of electrons between nonmetals. Do not get strong chemical bonds confused with attractive forces between molecules. What's a molecule, by the way? It is a group, a distinct unit of covalently bonded atoms. Do ionic structures make molecules? No, they make large crystal lattices.